In this video, we're going to talk about the equation for deflection. So deflection, we use the Greek letter delta equals our force times our length cubed divided by 3 times E, which is our modulus of elasticity, times I, which is our moment of inertia. We looked at moment of inertia in our last video, and modulus of elasticity is a material property. So deflection is dependent on material property and geometry, whereas moment of inertia was only dependent on geometry. Okay, modulus of elasticity is a value that you can easily look up online for different materials. For example, I just looked up online steel and aluminum has a modulus of about 29 million psi. Let's see, let me check, make sure I'm right here. Yeah, 29 million. Whereas steel has a modulus of, oh, you know what, I just mixed these up. Aluminum was 10 million and steel was 29 million. Now, in engineering terms, you wouldn't really use million. You would say maybe KSI or yeah, you would probably say KSI. So KSI is just PSI times 1,000, right? So PSI and then KSI. PSI stands for pounds per square inch, and KSI stands for kilopounds per square inch. So it's just PSI times 1,000. So 10 million PSI would be 10,000 KSI, and 29 million PSI would be 29,000 KSI. In engineering terms, that's usually how you do it. Now, this is English. If it was metric, let's see, the metric modulus for steel is about 200 gigapascals. So 200 gigapascals is, I think, 200 trillion. 1, 2, 3 is billion, million, and is that right? This is 1,000, million, billion, trillion. Yeah. But you would never say 200 trillion pascals. Pascals is the metric term for pressure or stress. A pascal is just a Newton per meter squared. So Pascal equals Newton per meter squared. But you would never say 200 trillion pascals. You would say 200 gigapascals, where giga refers to 9 zeros, right? So everything right here. Anyway, enough about units. Let's erase some of this stuff. And we're going to solve for deflection. We'll do something fairly simple, but why don't we let's still look at aluminum and steel. So let's say aluminum was 10,000 KSI, steel was 29,000 KSI. And since we covered moment of inertia in a previous video, we're not going to work out the math for that. Let's just say that we have an example where we've got a cantilevered beam like this, and I'm not even going to specify what the cross-sectional geometry or shape is, because that all goes into the moment of inertia. We're just going to pretend we've already solved for that. But we've got some force that's out over here. Again, this is fixed. And we've got a length right here, say length, and then our force. This is E right here, our modulus of elasticity. And now we're going to calculate our deflection. So to do that, we need a value for L, and the L, the length, is just the length from the fixed point out to the point at which the force is applied. So why don't we say L equals 10 inches. Now, when we did the moment of inertia video, we talked about how important the exponents are, right? Because they really compound these values, and we see that there's a 3 in the exponent place for our length. So we see there that our length is really super important in terms of how much deflection we get. If we double our length, what do you think? Is the deflection going to double also? It is not. If we double our length, our deflection will be exponentially increased to the power of 3. So we'll look at that in a little bit more detail, but length is really, really important in terms of managing your deflection. Okay, so if we were to solve this equation here, we would say, let's see, so F is, I don't know, what should we say F is? Why don't we say F equals 100 pounds force. So our deflection is 100 pounds force times 10 inches cubed divided by 3 times, and let's say this is aluminum, 10,000 KSI times our moment of inertia. Let's see, what do we want to say our moment of inertia is? I don't know, let's say our moment of inertia equals, we'll just say 10, make it life easy for us. And 10, it's going to be length to the fourth. So let's say it's 10 inches to the fourth, right? Because our moment of inertia is either bh cubed over 12 or pi d to the fourth over 64. Hopefully I've got that right. Yeah. So b and h are both distances. H is cubed, but b is also a distance, so it would be distance to the fourth power. And then for a circle, we've got a diameter to the fourth power, so our distance is also to the fourth power. And that's where we get our 10 distance to the fourth power here. Okay, so let's see. Why don't we just look at our units now, because this equation is getting a little bit more involved than some of the ones we've done in the past. So let's just solve for our units at first, okay? So we've got pound force times inches cubed over KSI is pounds per square inch. So we've got pounds force per inch squared. And then we've got inches to the fourth right here. So those are all of our units. Okay, so we can say that, let's see, these two cancel out, pounds, right? And we've got inches cubed on the top and inches to the fourth on the bottom. So we're going to be left with no inches there and just inches to the first power here on the bottom. But then we have this inches square. Since that's on the denominator inside a denominator, it's actually going to move up to the numerator here. We'll end up with inches squared here. And so now we have inches squared over inches, and the inches cancel, the square cancels at the top, this inches cancel on the bottom, so we're just left with inches. So our deflection is going to be termed in terms of inches, which is great. That's what we're expecting. Now let's go back and solve for the numbers. So we have equals 100 times 10 to the third is going to be 1,000. Right, 10 times 10 times 10 divided by 3 times 10,000 kilo, right? So we're going to add those 3 zeros back in here, times 10 to the fourth. So 10 to the fourth is, what, 10,000. So we're going to end up with a really big number here on the bottom. So check my math, 10 to the fourth, 10, 100,000, 10,000. Yep, that's right. Okay, so if we calculate this, it's going to be, let's see, we're going to end up with 5 zeros on the top, 100,000 divided by 1, 2, 3, 4. We got 4 zeros in 10,000, and in 10 million we've got 6, 7 zeros. So 7 zeros plus 4 zeros is 11 zeros. And then we're going to, 3 times 1. So 3 with 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a lot. Put some commas in there, clean it up. 3. Alright, so that's 300 trillion, I guess. Yeah, it's 1,000, 100,000. Oh, I may have messed up earlier when I was saying trillion. It would be 1,000, 100,000, million, billion. 300 billion, yeah. 300 billion. So earlier when I was saying 29 trillion, sorry, that was a mistake. Alright, so anyway, we've got 100,000 on top and 300 billion on the bottom. So we can remove some zeros, cancel 5 zeros on top. 1, 2, 3. Maybe we'll do these 1, 2, 3, 4, 5 here, and we're left with equals 1 over 3. And we've got 3 million. 1 over 3 million. So a very, very small number. Let's see, 1 divided by 3 million is yeah, that's a very, very small number. So basically, we're not really deflecting at all. And that's assuming that our moment of inertia is 10. Let's see. What does a moment of inertia of 10 actually look like? I'm curious now here. Let's say our base is 1 and our height is 2 or something. 1 times 2 times 2 times 2 is 8 over 12. So 1 times 8 equals 8 over 12. So that is what? 2/3 equals divided by 4. Yeah, 2/3. So a moment of inertia of 10 is actually pretty high. Maybe we use something that's too high, but even with that, let's see, that would be a base of 1 inch by 2 inches. So we'd have a shape, cross-sectional shape of our beam that looks something like that, which is pretty big. So let's see, what if we say that our length is 1 and our height is only 1/4 of an inch? Then what do we have? So our BH cubed would be 1 times 1/4 cubed over 12. Let's see what that is. So 0.25 times 0.25 times 0.25 equals that. And times 1 on the top, no difference there, divided by 12 equals that, 0.0013. So equals 0.001. Alright, so now if we kind of redo this here, I want to get a deflection that's actually measurable, just, I don't know, just for fun here. And maybe let's use 1,000 pounds of force instead of 100. So we'll have 1,000 pounds of force times our length. Let's say instead of 10 inches, we do, let's do 100 inches. So that's a lot longer. 100 inches cubed divided by 3 times 10 million, because we're going from KSI down to just PSI, and then times I, instead of I equals 10, we're saying I equals 0.001. Okay, so now what do we have here? We've got 1,000 10,000 times 100 cubed. Whew, that's going to be pretty big. 100 times 100 times 100 is 1 million. So 1 million divided by 3 times, we got 10 million times 0.001. So 10 million times 0.001 is, let's see, was that just 10,000, I think. Let's 10 million times 0.001 equals 10,000. So go back here and say 10,000. And now, let's see, we may have gone too far in the other direction, but if we cancel out some zeros here, see 3 and 4, and 1, 2, 3, 4, and now we're left with, let's see, 100,000 over 3 equals 33,000 inches. Okay, so 33,000 inches is obviously not realistic. This beam would just break before then. So we've gone too far in the opposite direction. But you can see how important L is, right? When we went from 10 to 100. In fact, maybe we should try. Maybe all right. Third time's the charm, right? Let's do this with just 10. A length of 10 again instead of a length of 100. So then we have 100 pounds force times 10 times 10 times 10, right, which is 1,000, divided by 3 times, I'm going to simplify the bottom here. Last time we saw that 10 million times 0.001 was just 10,000. Okay, and now if we get rid of 4 zeros, so 1, 2, 3, 4, now we're just left with 10 divided by 3 equals 3.33 inches. So now we see that if we place 100 pounds of force at the end of a 10-inch long beam, and this beam is 1-inch base. Let's see, so it's like 1-inch base by 1/4 inch height. It would deflect by 3.33, which is also actually pretty big for what we're talking. I'm sure that would plastically deform it, and we're not going to get into this, but once you plastically deform a material, this equation actually is no longer valid. Material starts behaving differently beyond its plastic deformation point. This equation is only valid when the material, the object, is within its elastic range. And then beyond that, it's a whole new ball game. But we're not going to get into that. That's much more complicated. And honestly, it's not something that's used very often, because if something is plastically deforming, we're probably not very concerned with how much it's deflecting at that point, because it's plastically deforming, and that is usually a bad thing. And so we just want to stop there and say, okay, back up. We need to change something because we don't want this to plastically deform. So 3.33 inches, you know, that's probably beyond its plastic deformation range, which means that answer isn't even really valid. If we ended up with something like, I don't know, a 1/4 of an inch of deflection, you know, that would be something that's very valid, because I'm sure a 1/4 of an inch out at a 10-inch length is well within the plastic deformation range of an aluminum bar. And you can see how doing the math on this, it takes a little while, and it can be kind of monotonous. And oftentimes when you're designing something, you want to be changing really quickly. You know, this is actually a good illustration. You know, when we got these numbers that were just crazy, right? Like no deflection at all at first, and then we had this like 33-inch deflection or whatever it was. I think it was a lot more than that, actually. But we get these crazy numbers that just don't make sense. And if we're designing something, we want to really quickly be able to iterate on our base and our height and our length to find a set of values that that produces a deflection that we can live with. And, you know, oftentimes you have a max deflection in mind that you want to stay within. Maybe you want to make sure that you don't go past half an inch of deflection for whatever reason. So you want to adjust your base or your height or your length so that you're less than half an inch of deflection. And if you have to go through by hand like this and do that every time, it's cumbersome, it's prone to errors, right? Just doing math by hand is not efficient, and it's risky because you might make a mistake somewhere. So this is where you use a spreadsheet. You program a spreadsheet to do all the math for you, and then all you have to do is change your variable. You know, change the value for B, change the value for H, change the value for L, and your answer, your deflection, will just update automatically, and it takes, you know, seconds instead of dozens of minutes, and there's no or at least much less chance for error. And that's where the power of a spreadsheet comes in, and we'll talk about that in a future video. But for now, that is how to calculate the amount of deflection on a beam, or, you know, some member on which a load has been applied. If you found this content helpful, consider enrolling in our signature program at mypipelineacademy.com. Whether you're an individual interested in beginning a new career as a mechanical designer, or a company interested in training your new engineering hires, our signature program helps students develop the practical skills they need to be productive mechanical design engineers. Seating is limited. We hope to see you there soon.